Hello, my name is Rob Reynolds. Welcome to Mat-073. Today we get our last section, 7.8. We're going to be solving quadratic inequalities today. And I'm going to show you a method that I think is a little bit different than the book. We're going to be using our graphing calculators as well. So quadratic inequalities look like equations, but inequality just means I have a greater than sign or greater than or equal to sign. So if it's just a greater than sign, then it's like an open dot. If it's greater than or equal to, it's like a closed dot. It could be equal to that point. So first of all, let's look at the greater than sign. The first thing I would try to do is factor this thing and then set each factor equal to 0. So factors of 8 that differ by 2 are 4 and 2. Signs are different. The larger term is positive. So I'm going to call these critical values. Negative 4 is a critical value because it sets it equal to 0, and I want to find things that are greater than 0, and 0 would be the breaking point for that. I'm going to go to a number line and evaluate negative 4. Remember, it can't be equal to negative 4, and it can't be equal to the 2, so it's kind of like open dots there. But then I'm going to use my graphing calculator and kind of quickly evaluate some points, and plus I kind of want to check the graph anyways. So x squared plus 2x minus 8, I'm going to hit trace, and I'm going to check a point out here like, f of negative 5, and I'm really interested in these points out here. Are they going to be greater than 0 or not? So if I hit negative 5 and press enter, I get a 7. So then I make a conclusion. Well, is 7 greater than 0? And I say, yeah, true. So I know that area is true in here. I'm going to test 0. And I get a negative 8. Well, negative 8's not greater than 0, so that's a false statement. And the last one I'll check is maybe a 3. Anything to the right over here would be fine. And f of 3 turns out to be 7, and well, and that's greater than 0, so that's a true statement, true. So I would say that the solution is everything over here, which is negative infinity up to negative 4, this critical value, but I can't include it because it's just greater than it, not equal to it, in union with everything from 2 to infinity. And if you look at the graph, it's kind of like you have open dots here, and you're including everything over here and over here, but then again, there's final solution in interval notation. You can pause the video here and read the book's step-by-step procedures, but I'm just going to keep going here and say, hey, factor completely and find some critical values and set them equal to 0. Even though this is less than or equal to 0, I'm going to think, when does x equal 0 and when does x squared minus 9 equal 0? And of course that happens at x equals plus or minus 3. Go to a number line, and in order from least to greatest, let's put some critical values, and let's test, like f of negative 4, f of negative 2, f of 1, and f of 5. Any number to the right would work. So I'm going to go to my calculator and quickly evaluate x cubed minus 9x. I'm going to ask it to trace, and I'm just going to quickly evaluate f at negative 4. So I'll hit a negative 4, press enter, and I get a negative 28. And then I ask, is negative 28 less than or equal to 0? And of course that answer is true. Then I'll plug in my negative 2, and I get a false because there's the 10, and 10 is not greater than or equal to. A 1 is negative 8, which is true, and a 5, which is back to 80. What was the 1? Yeah. Any negatives is true, so this is a true statement here, and this would be 80, which is a false. So my true statements are here and here, but be careful, this is an equal to sign. So now I have brackets. So from negative infinity up to negative 3, but this time I can include the negative 3. I can never include infinity in union with brackets 0 to 3. So how do I know that it's a bracket? Well, I can include it. It's kind of like having a closed dot there opposed to an open dot. So here's the book solutions, and here's all their tests, but they get the same, there it is, the same solutions in interval notation. So again, you can pause the video and kind of read how the book suggests solving these, but I'm going to keep going. So if you have a critical value down here, which we do, we know critical value immediately is x equals 3, because if you let x be 3, that's divided by 0, and 0 is an undefined value. So automatically the denominator is a critical value, and I would say not only is it a critical value, it's going to be an open dot, because I cannot let x be 3. So I can let it be right up next to 3, but not 3. So then I'm going to treat this as a new problem. It's kind of like x plus 5 over x minus 3. I just want to know the critical values equaling 3 over 1. So I'm going to do some cross multiplying here and set the two diagonals equal each other. So 3x minus 9 should equal x plus 5. This is the green diagonal equals this diagonal, which is just x plus 5. So 2x is equal to 14, and x equals 7, which is my other critical value, which, by the way, since this is an equal sign, then I think about this being a closed dot. So I kind of like to put the open dot and the closed dot down here to kind of remind me, because I usually forget whether these are open dots or closed dots by the end of the problem. So sometimes you might want to just give yourself a little heads up and mark your graph with either an open dot or closed dot, so that when you get to the end you'll know, oh, that's the parentheses and this is a bracket. Sometimes confusing. So let's test like, oh, f of 0, anything between 3 and 7, like 5, and then f of 8 would work for me. A little bit tricky to type this into the calculator because you're going to have to use parentheses. So I'm just going to type in the left side, x plus 5 divided by, and make sure you encase the denominator in parentheses too. If you don't, you'll get a bad graph. And I'm really just interested in evaluating at 0, 5, and anything to the right of 7, like 8, and seeing if it's greater than or equal to 3 is what I'm interested in. So I'm going to test to see if these evaluate greater than 3. So the y value is negative 1.6. That's false. The y value here is 5, and 5 is greater than 3, so that's a true. And if I test anything to the right, like 8, I get a 2.6, and 2.6 is greater than or equal to 3. This is actually a false statement. So the only true places that I have is between 3 and 7. So remember, it's a parentheses and a bracket is the only true region that I have. Here's how the book chooses to find the critical values, and they talk about the interval, and then they run all their tests by actually, I would do all of this on the calculator, but if you want a number crunch, you certainly can. But again, I think the only true one is this one, and so their final solution again is between 3 and 7. Remember, you can't let x be 3, that's why there's a parenthesis there. Again, immediately I see that there's a critical value here, 4x plus 3 equals 0. When 4x equals negative 3 or x equals negative 3/4. So immediately I've got an open dot at negative 3/4, and I would label it open dot. Moving on, I've got, I'm going to treat this like an equal sign, so 5x, oh, excuse me, 5 minus 2x, 4x plus 3 equals 0 over 1. So this diagonal just goes to 0. And this diagonal is the only one that I'm interested in. And this guy is going to be, what, 5 minus 2x. So if I add 2x, I get 5 halves is my other critical value. And since this is an equal sign, then it's a bracket or a closed dot. 5 halves. So I'm going to run some tests like, oh, f of negative 3, f of 0, and f of, well, 5 halves is 2.5, so anything to the right of that, I'll try a 4. So begin, again, be careful typing this in. I would use parentheses, 5 minus 2x divided by, in parentheses, 4x plus 3. I'm going to trace and check negative 3, 0, and anything to the right of 2.5. And I'm checking to see if it's less than or equal to 0, so I'll test negative 3, and look at the y value. It's a negative, so that's less than 0, so that's a true statement. Let's test 0. 1.6 is not less than 0, so I'm looking at the y value. So this is a false statement in here. And then I'm going to test the 4, and that's negative, and all negatives are less than 0, so that's true again. So my true is here, and here is my shaded. So to list the final solution, this goes from negative infinity on the left all the way up to negative 3/4. That tells me that's a parentheses. Never put a bracket on infinity. In union with, but this closed dot reminds me that it's a bracket. 5/2 up to, and this must go to a positive infinity. We'll see if the author agrees, and yes, they do. So I have the last example here. The key here is to factor everything completely. I think this factors to x minus 6, x minus 5, factors of 30 that add up to 3. Factors of 9 that differ by 8 are 9 and 1. Signs are different. The larger term is negative. So immediately I know that I have critical values of negative 1, which is an open dot, 9, which is an open dot, because that's what causes the denominator to equal to 0, 5, and a 6, which are closed dots. And then I would grab my calculator and run my tests. I think this region will be true. This will be false. This will be true, false, and then this region will be back to true. Notice that they alternate, and that's always going to be the case unless there's a double root. So be careful. I should have shown you an example. A double root would be something like x plus 3 quantity squared. And that means it's not going to alternate from true to false or true to false, or if you have any even exponent, it'll go true true or false false consecutively. But since they're all to the first powers, they should alternate true false true false. But remember, double roots, we've talked about this earlier. If you have a x plus 3 quantity squared, that should come down here at negative 3, and that will bounce off. So if this is positive, this will remain positive. So be careful of the double roots. I didn't show you an example of that. But here's the final solution. Remember, be careful of your parentheses in union with, this is going to be brackets here because these are closed. And then we're back to a parentheses, 9 to infinity. And the author agrees. All right, so I should have had one more example where we had some double roots, but maybe your My Math Lab will cover that concept. Good luck. Email me with your questions.